Okay, now we have reviewed until our polar coordinates, how to get the polar curves at least. And I also attached additional video from other sources, and I think it's quite easy to follow how to draw and how to sketch. I will show you later another curve that we can sketch. But maybe we can have review on the previous sections before the polar coordinates, okay, the parametric. I just want to let you know what we are having on the parametric. Okay. So let me put the, okay, let me put here. Let's say this is the questions. Okay. So let's try to solve together. Okay. And I think the question is asking directly, straightforward, right? You can read the question first and try to understand the question. This is one of I think typical question in parametric. So it's asking a point. So it's asking a coordinate. At what point on the curve x equals 3t squared plus 1 and y equals t cubed minus 1 does the tangent line have slope 1 over 2? So the slope is half, and you know the parametric equation, and I think it's kind of direct questions. Okay. Okay, anyone solve which point? Which point? 4, 0. Okay. Okay. So let's check. Okay, let me write the x is 3t squared plus 1, and the x dt, then it becomes 60. Y is 3 cubed minus 1. So dy dt is some common mistake on the students that I see in the previous years, that if you want to have the tangent, that is the dy over dx, you put wrong equations. You put x here and y here. So that is a common mistake that still happen. So the way is, this should be dy over dt, and this should be dx over dt. So be careful to check the equation before you put in. So this is become 3t squared and 60. So we have, this is half t, right? Or t over 2, that's also correct. And we know that the dy over dx, the value itself, based on the question, is half. So we know that half t is half. So this happens when t is equal 1. So at t equal 1, we will have x equal 4 and y equal 0. So the coordinate that we want to have at those slope, or the tangent, will be 4, 0. Okay. Okay, I'll just give you some quick question. Okay. The other question is this area. Okay, area of the region. Let me give you a few minutes to try. Sorry. Okay, the key for the parametric, okay, or even in polar, because most of the graphs or some of the graphs, like in parametric, they will have some certain degree of symmetry. You see the symmetry, right? The symmetry. So you see this. This is perfectly mirror this one, right? So to evaluate, we can take the half, only half the area, and then multiply by 2. Okay, anyone have the solution or calculation? Okay, so first we can look on the parametric itself, and we can decide which t that is correspond to the axis in the parametric. So at least we would like to know this part and this part, right? Or we can write first the Cartesian integral, okay, to C. So we can write the area as twice of from 0 to 1 of our y dx. Okay, we can write first this. Okay, this is the key, first the key. Okay. And then we would like to know which part of t that has equal 0 and 1 in x. Okay. So this is x, right? based on here, right? So this is this is our functions of x, right? Okay. Now, from here we can convert into parametric. Okay, parametric. So the parametric, we can look on so x intercept. It can be 0 and it can be 1, right? So based on the parametric, this will be the so t squared equal 1, and then t equals 0. Or t here is plus minus 1. But then we have also y that is a 0, right? Y is 0. So we would like to write down the parametric. So t or 1 minus t squared. Or this will be 1 minus t. 1 plus t. And again, we get 0 and 1. And we need to restrict our t from 0 to 1. So when x 0, t is 1. And when x is 1, t is 0, right? So this is going to be here, right? So the area, we are now changing to t, which is from 1 to 0. This is t. And then changing the integrations inside becomes y. Let me just write y t, and then let me just write x prime, or dx dt. You can write also the. Let me just write maybe dx dt. I think better to write like this, and then dt. Okay. Now dx dt is minus 2t. So we can write 2 y is t minus t cubed, and then multiply with negative 2t, and then dt. Maybe I need to write a little bit left. Okay, maybe we can write here. So this will be negative 2t squared plus 2t with power of 4 and dt. So this will be 4, and then the inside will be 1 over 5 t with power of 5 negative 1 over 5 t cubed from 0 to 1, from 1 to 0. So this will be this should be 3, right? Should be 3, yeah. Well, I'll write 5, okay. Okay, and then should be negative. Let me check the negative signs. Negative 2t squared. Yes, it's correct, right? But if you would like to change the minus and plus, that's also fine. You can change to this also. I think this is also okay. And change the 0 to 1. I think this, sometimes, I know some students have some difficulty on the plus minus, but I think sometimes you can exchange the positive and negative to make it 0 to 1, so that I think in calculation it can avoid some calculation mistake. So this should be 1 over 3 or 15. This should be 2 over 15, so it should be 8 over 15. Okay, let me write maybe here 8 over 15. Okay. Okay, so the answer is 8 over 15. Okay. Later, probably I will give you some practice, maybe 5 or 6 questions. But let's just continue to our polar, and then the calculus polar. Okay, any questions before? Okay, I think still okay. Okay, so the key important in the area first is usually finding relations or finding the interval of t. Okay. The second is write at the beginning. Okay. And then 3, convert to the integral and I think most of the case this will be the steps. Okay, so first probably write either 1 or 2, write the integrations, find the interval of t, and then convert the integrations to the parametric integral. Okay, so you change all into t. Okay, the variable will be t, so from x to t. But sometimes maybe it can be also dy, so you can adjust by yourself. Okay. So if dy, then should be xt dy dt. Okay. Okay. Now the last part in our course is we have draw some of the polar curves. Let me add an additional graphs. That is the r equal cosine 2 theta. Okay, maybe we can draw the original graph that is in Cartesian. So this will be the r, and this will be the theta. Maybe it's too small. It'll take longer. So let's connect all the points. Probably that is our curve, right? Okay, based on the value and the theta, we try to graph this into our polar coordinates. So first, maybe draw the axis like that. And then stated that this will be theta equals 0. This is theta equal pi over 2. This is theta equal pi. And this is theta equal 3 over 2 pi. Okay, now based on the value, right? At theta equals 0, the radius is 1. So if we have radius 1 here, maybe this is 1. Let's say this is 1. Okay. So we start from here, from 1. And then we are going to have some decreasing value, right? Some decreasing value up until pi over 4, right? Up until pi over 4. So maybe we can have some angle that shows the pi over 4. So it should be at the middle part here, right? Because every pi over 4, they will go to 0, right? Okay, let's say that's our line. So this line is theta pi over 4. This is maybe theta 3 over 4 pi, and the other theta as well, as long as it's adding pi over 4, pi over 4. Okay, now the graph will start from 1, and then it decrease, and then 0. It should be perfectly aligned like that, maybe. Okay. And then where we will go after 0, we will still decreasing, right? Still decreasing until -1, right? Until -1. Now we have the radius is negative. Okay, radius is negative up until the pi over 2. So pi over 2 is negative. So where we are going now? So at pi over 2, it should be -1. But because it's negative, it should be goes around here. The opposite sides, right? And if you connect all, I think it's too short. Let me make a little bit, maybe here. Okay, maybe it's more equal. And if we connect all, and then this will be going through here. And this is going through here. And this will be going through here. Let's do both. And then going through here. Yeah, so it's it becomes like a flower. We call this, the name is rose. So because it has 4 leaves, we call it 4-leaf rose. Can you imagine what will happen in sine 2 theta? It will rotate a little bit, right? Rotate a little bit. And it's become like this. Right? Like a rose, like that. Rotate a little bit. And if you check the pattern, this is when they have the even numbers in petals. Like if this is cos 2 theta, if you have cos 4 theta, it will be 8-leaf rose. And it will have some patterns. Okay. But if it is an odd, like from 3, 5, let's say we have cos 5 theta, it's just 5 petals or 5 leaf rows. Leaf or petal, it's the number in the flowers, right? So every odd number, it will be 3, 5, 7. But if it is an even number, it will be 2, 4, 8, 6 also. Okay, but that's not really that essential in our class. Okay, but at least you know how to get the curve. Okay, another way, if you would like to check on your own, like maybe you check some functions you get from a textbook or from other, you can go to, let me show you, go to the GeoGebra. I think you can check the polar curves. There are some activity that you can do, but I would like to suggest the polar coordinate system. They are already prepared. Someone already prepared for you here, so you can check the polar coordinates. So this is the polar coordinates. Like I said, we have like circle and circle and circle. Okay, if you can input maybe the cos, let's say we have maybe from 2 theta that we did, let's say the theta. Okay, oh, it's really small. Okay, really small because it's only 1, right? The radius, it's only 1. That's okay, very beautiful, right? If we check maybe sine 2 theta, right? It's a little bit rotated, okay? And if we have maybe let's say sine or maybe a cos 3, oh sorry, 3, let me just erase this first. Okay, okay, now 3 is like that. Now let's try 5. It's much more easier using this one rather than drawing with your hands, right? So it's 5 now. So like we have like 5 petals or 5 leaves, and every odd, it will have like exactly the same number as the number in the functions, like 5, 3, right? But if it is like even, like 2, or maybe let's try 4. it's 8 petals, right? It's twice as much as the number in the functions, right? And even we can check any polar that we can think. Maybe the let's say 2 plus or minus cos. This will be the limason that I think we mentioned in a brief, okay, limason. And there are some or several family of limason. We can have maybe 2 minus, let's say 3, and then cos. Okay, look at this. We change a little bit, and we get this another limason. And if you look this limason, it has the value is -5, the maximum value. Of course, that's negative is actually a positive. Okay, but this is to suggest what's the idea behind the additional 2 and 3. The maximum that cos can have is 1, right? Cos 0, 1. And then it can also be a negative. And we can see that it can have some combinations in terms of a number. Okay, so that's you can check and play with this actually. Okay. So you check the GeoGebra and look for the polar curve, and you can find this type of graph. I think a little bit scrolling down, and you get to know the polar curve. Okay. Okay, back to our notes. What I would like to summarize is let me check. Okay, this is the limason. Last time we did the 1 plus sine, right? 1 plus sine theta. Now if you look here, this family of a polar curve of limasons. This is limason of 1 plus c sine theta. Okay, so you can write 1 plus c sine theta for a general equations. And if you change c with some constant from positive constant to a negative, you will see the difference. Okay. When we have c is 0, it's a perfect circle, right? Perfect circle. When we are increasing the constant, like first is 0.2, and then 0.5, 0.7. You see the circle kind of moving. It moves up, right? And then it's again moving. This is called we already called this is a convex limason. And then it has like a dimple here. We call this a dimpled limason. And then when it's equal 1, what we did last time, this is the cardioid. And then when it is greater than 1, we have, this is called inner loop. So it has a loop inside. So we call this is inner loop limason. And we increase greater than 2, the inner loop getting bigger. Okay. Similarly, when we are reduce the constant, it's become negative. It's getting down, right? It's getting down here, and it's getting a dimpled, and it's getting a cardioid, but different sides, right? And it's getting an inner loop. Okay. So at least you have 1, 2, 3, 4 types in a limason. If you maybe not really good at looking at this number, we can check with we can write in terms of A, plus minus b sine theta, or the cos one. And every cos and sine, the difference is like in the circle. If you have cos, you will have, right, this is a positive cos. And if you have a negative, this will be the negative cos. Okay. And if you have sine, the patterns should be the same. This is the positive one, and then this will be the negative one. Okay. So this is plus minus cos, this is plus minus sine. And the terms plus and minus will also appear in the limason or the cardioid. Okay? If you see it's having much more portions in the top, then it should have plus. Okay? It should have plus. Maybe 1 plus something or 2 plus something sine. Okay. Okay. And from this AB, we can have like AB, is that equal 1? Or AB maybe greater 1, or AB is less than 1, okay? Or even AB greater than 2, or A over B less than 2. Less than 2, I think not really important. Okay, now in general, okay, last part in the polar coordinates before we go to the calculus is the, okay, I think this one. Just a summary. The common polar curves that we are going to find in our course. Okay, the circle or a spiral, even the spiral, the right one. So it's spiral here. And the limasons, you see the A plus B has A slash B, A equal B, A greater B, okay. And then this is convex limason. It's kind of getting closer to circle, but it's not a circle yet, okay. So it's like, it's kind of, this inner loop is moving and then goes up until this point, and it's moving, it's going to be dimpled and then moving out and make it a circle. And eventually when it's when B is 0, and then it's getting a circle. And roses, you have the pattern for the odd or even for the n, okay, for the n inside the function here. 4-leaf rows, that is what we did. And then this is some example on cosine. Okay. In terms of sine, you need to rotate a little bit, pi over 4. Okay, rotate pi over 4. So this will be the, if I like to write maybe here, this is the sine one. And this will be the third, and then this is yeah, and then you can imagine it will be really crowded like that. Okay. And the last one is the lemniscate. It's only having two typical forms, the sine form and then the cos. Okay, and the formula is just a squared sine 2 theta. Okay, and just these two forms. Okay. Okay, I think that's most of polar that we can check and observe. Actually, there's other, like, can we combine the polar between? Yes, we can combine, but that will be a little bit complex and complicated. But we can combine. And you can check in the GeoGebra if you would like. We can combine some polars. Like, for example, you have 1 plus sine theta, right? You can check 1 plus sine 3 theta or sine 4 theta. So we're combining the limmason, right? And then we're combining the rows. So it's a limmason, but it has a petal, so it's recycling the patterns. Okay. Yo, what happened? Okay. Okay, don't worry. Okay. Just leave it be. Okay, let's move on to the calculus in polar. Oh, do you have any questions first? Any questions? Okay. Okay, the first approach for the calculus in polar is from the circle. Okay, and then we divide the circle and describing the sector. Okay, this is called the sector. So let's say this is having a radius r, and we have certain angle theta. Okay, so let's imagine like when you divide pizza with your friends and you want to have a bigger pizza. Okay, so the area of sector, we can use the angle ratio, right? Theta divided by 2 pi and then pi r squared, right? And we can get this is okay. Okay. Now this area we are going to use to approach in a area in a polar. Okay? Area in a polar. So if you have a polar curves and you would like to know the area under that polar curves, we can go by this method. But of course, we would like to establish the rule or the formula, right? So let's start with something random. So let's say we have a curve like that, and we have maybe different color. Okay, we have angle from here. This is, let's say, A, and this is B. Or we can say the angle, this is theta equal A, this is theta equal B. Okay, and this is the curve R equal functions of theta. And the middle part is just our region. Just our region. Okay, if we define like we define the integral in calculus 1, we define into usually the small rectangles, right? We define. But here we define in a small sector, right? So we define, and let's just took one sample, and maybe here. Okay, so here's the example, okay, and the area will be inside the circle but outside the cardioid, so it will be here. Okay. Now to evaluate first, okay, in the polar, what we need is we need to know the interval, right? The interval of the angle. So first, we need to check this interval, at least one, because it's again because of the symmetry, we can evaluate from this blue cross here. We can evaluate until pi/2, and then multiply by 2, right? Or we can first maybe evaluate this blue and this one, right? That's the total area, right? And then we can take the circle, the function in the circle, minus the cardioid, right? Okay, so we can write, maybe let me write first, and then you can see how it works. Okay, so first we can write down, or maybe we can check the intersections. So intersection will be 3 sine theta equal 1 plus sine theta. Or we will have sine theta equal half. Okay. So theta will be from pi/6 and then 5/6 pi. The difficult part in most of the polar curve is to imagine how from the graph and then transform into our formula. That's the difficult part. The formula that we are going to use is just half r squared d theta. It's always like that. Okay. So the area here will be A. Okay. The area of polar. Okay. For the circle, this will be the formula, 3 sine theta and then squared d theta, right? So this is a circle. And then minus half from pi/6 to 5/6 pi, 1 plus sine theta, and then squared, and then d theta. This is the cardioid. Okay. Now we can also write in terms of, because of the symmetry, because of the symmetry. Then we can write a. Because it has half, I can multiply 2. Okay. So this will be from pi over 6 to pi over 2. And then the half is removed because multiplied by 2. And then this will be 9 sine squared theta d theta. Let me just maybe write one by one. This will be 1 plus 2 sine theta plus sine squared theta d theta. Okay, and then we can have and again, I think you can finish this by yourself. And this sine squared here, we can go back to our cos double angle formula, right? So it would be 4 cos 2 theta. Okay. Okay. Or we can write, this will be 3 minus 4 minus 2 sine. Okay, don't forget, okay, if you have this cos 2 theta, don't forget to divide by 2 when you integrate. So this will be 3 theta, negative 2, sine 2 theta, plus 2 cos theta. And plug in the pi over 6 to pi over 2. Okay. Okay, now, in general, when we have two polar curves, right? So this is the r f of theta, and the other one maybe here. Maybe this is g of theta. And then if this theta is A, this theta is B. If this is the area that we want to evaluate, then we know that the f is greater than g, is greater than 0, and the angle is between 0 and 2 pi. Then the area we can write or we can write all in one terms. So generally we can write like this one. Okay, we may have some review next Thursday. We can have some practice, one or maybe two questions. So I can finish the area, and then after the area, arc length. Okay, so this is all the area. Now we move to the arc length. Okay, arc length. Okay, remember that we have the relations between Cartesian and the polar. We can write like this, or in terms of function of theta, we can write the r as a function of theta, like this. And also for y, we can have r sine theta. Right? Now, to find the length of polar curve, to find arc length of r f theta, function of theta, and theta is from A to B. Okay, we start from derivative of x and y, and we derive with respect to theta. And because we have functions of theta, both of this, then we can use the product rule. And take this as, I just write as r, okay? So dr dt cos theta, and the other way around is sine, r sine theta. So let's start with this, okay? And then we try to square this one. So we square dx over d theta and dy over d theta, okay? Because remember, in parametric, we already know how the arc length, and it has a squared, right? So let's just square this too. And then we combine those two. So we can write dx over d theta squared plus dy over d theta and then squared. Okay, so let's write one by one. So dr d theta squared cos squared theta minus 2r dr d theta cos theta sine theta plus r squared sine squared theta. Okay, this is the first one for dx over d theta. And then plus dr over d theta squared sine squared theta plus 2r dr over d theta sine theta cos theta. And then plus r squared cos squared theta. Okay, enough. Okay, enough here. Okay, this part here is canceling, right? Okay. And then the other one, if we look at, is dr over d theta squared, dr over d theta squared, and it has the cos squared and sine squared, right? So we can use sine squared plus cos squared equal 1. So we have only dr over d theta squared. And the other one is this one. So we have plus r squared. Okay, so we can simplify these terms, convert into polar, and we have these expressions. Now, okay, from these expressions, remember that we already established the parametric arc length in parametric. We can write first. Okay, we can write first. This is equal right. Usually it's t, now it's theta with the same parametric. And then we can convert this using our expressions on polar. Okay. Okay, now okay, let me just finish. This is the arc length. I think we can finish just a tangent, and we can review and having exercise next Thursday. Okay, so let's move to the next one. So this is the tangent. So it's quite unique. The parametric start with tangent and then area and then arc length. By polar, we start from area, arc length, and then the tangent. Okay, it's similar to the arc length. So we start with the relations from Cartesian to polar. Okay, and then the same thing, using the product rule, we can get the dx over dt, right? We can get the dy over dt. But let me combine directly into one formula. That is the dy over dx is equal dy over dt, d theta, okay, sorry, and then dx over d theta. So this will be dr over d theta sine theta plus r cosine theta. And that's practically the tangent. And in the tangent, we can have the horizontal and the vertical, right? So we can also look on these terms. Let me just write one more here. So horizontal tangent this is when dy over dx is equal 0, which means dy over dt or d theta is 0, and dx over d theta is not 0. And then similarly, we can also locate the vertical tangent. This is when dx over d theta is 0 and dy over d theta is not 0. Okay, so if we look here, if we have r equals 0, what will happen? So the tangent will be precisely just this over this, which practically just a tangent theta. So this is a tangent line at the pole. Just to give you a brief idea on why we are usually naming the tangent as tangent. Okay. Aside from the tangent means to touch one point. Okay. Okay, maybe example. Okay, an example before we end the class. So let's say we have a cardioid. We already sketched and drawn the 1 plus sign. Find the slope. Okay. Find the slope when theta is 5/3. And then find the points where tangent line is horizontal or vertical. So the first question is finding dy over dx. Okay, finding dy over dx. Okay, so first we can take the equations. We can put into our equation like this. Okay, and then based on what we have in these equations, 1 plus sine, dr d theta is just a cos, right? So we can write here, maybe here, it's just cos theta. So we can write into our equations, this is cos theta sine theta plus r is 1 plus sine and then cos and then divide. This will be cos theta minus 1 plus sine and then sine. Okay, we can simplify and then try to check the equations. This will be 1 plus 2 sine theta, and the bottom will be this will be cos squared theta minus sine theta plus sine squared theta, right? So it should be 1 plus sine right? We can write down like this. So we can write in terms. Okay. Now instead having the looking at this formula, if you remember the parametric equations, okay, how to derive using the calculus in parametric, if we go back and write it down from these terms, okay, we can write down and then we can simplify this, become this will be cos theta plus this will be sine 2 theta over 2, right? This is cos theta plus sine theta cos theta, where the sine 2 theta is 2 sine theta cos theta, right? So from here we can write like this. And for y, we can write 1 plus sine and then sine. And we can write sine theta plus sine squared. Okay? And then from here, we can write dy over dx. And then we can derive each one and then put into our equations. This will be dy over d theta and then dx over d theta. Okay, so it's basically a parametric. Okay, basically it's parametric. And I think it's you can stick to this one, okay, instead of using this one. But it's resulting the same results. Okay. So we can have, this will be directly deriving these y, okay? So this will be cos theta. And then sine squared, we can take it to the double angle formula. And it will be 2, or we can write 2 sine theta cos theta directly. Okay? And dx over d theta will be minus sine plus cos 2 theta, right? And we can take this as in sine 2 theta and then minus sine theta plus cos 2 theta. This is actually equal with the previous one, although it's not really similar, but you can exchange and find that it will be equal. So either way, either method, both methods are fine. You can check, or using just one that's fine. So you can directly using the this polar dr over d theta. Or you can using the parametric approach. This should be the same. Yeah. Okay, so the slope of the tangent. Okay, slope of the tangent at let me write here. So at theta equal pi over 3, if we plug in the value, it will be resulting dy over dx equal -1, right? I think I will just finish until here, and we can continue the rest in the next